What if I told you that everything you experience, space, time, gravity, the fabric of our reality, might just be an illusion? That the three dimensions of space and the one of time that we move through every day might not be fundamental at all, but a projection, a hologram. This isn't science fiction. This is a real idea from cutting-edge theoretical physics known as the Holographic Principle. And in today's video, we're going to explore how black holes, quantum mechanics, and string theory all point towards the mind-bending possibility that the universe we live in might actually be a shadow of something deeper, simpler, and flatter. Our story begins with black holes. Not just terrifying cosmic vacuums, but actually nature's ultimate hard drives. In the 1970s, physicist Jacob Bekenstein proposed that a black hole's entropy, a fancy word for the amount of information it can contain, isn't proportional to its volume, like you'd expect. Instead, it's proportional to the surface area of its event horizon. That's weird. Imagine cramming more and more data into a USB stick and finding out its surface paint tells you how much it can store. It doesn't really make sense, unless we're thinking about reality the wrong way. Stephen Hawking later confirmed this with his discovery of Hawking radiation, that black holes slowly evaporate, leaking information. But this opened a paradox. Where does the information go? If it disappears forever, that breaks quantum mechanics. But if it escapes, then how? This puzzle led to a wild idea. Maybe all the information about what fell into a black hole is actually stored on its surface, the event horizon, kind of like a hologram. And that's where physicists Gerard Hooft and Leonard Susskind took things a step further. If a black hole can encode 3D information on a 2D surface, maybe any region in space can. Imagine a fish tank. You'd think the information about every water molecule in the tank is stored inside. But what if everything happening inside could also be fully described just from the data on the glass walls? That's the heart of the holographic principle. The idea that everything in our universe, particles, forces, and even you, could be described by data on a lower dimensional surface. But how is that even possible? How can a flat surface store a full 3D world? Let's step back and talk about field theories. Picture a 2D grid, a pixelated plane. You assign rules to how those pixels interact. That's field theory. Now, if the rules stay exactly the same, no matter how much you zoom in or out, that's called scale invariance, like zooming in on a fractal. A field theory with scale invariance is called a conformal field theory, or CFT. The magic trick is this. When you add scale as a kind of extra number line at every point in the grid, the system starts behaving like it's living in 3 dimensions. Now we're seeing how a 2D surface can give rise to a 3D world, just by adding this hidden dimension of scale. It's like a secret direction encoded in the rules themselves. Now let's bring in string theory. So originally, string theory tried to describe particles like quarks bound together by gluons. Tiny strings vibrating in different modes. But when you write out the math, something strange popped up. If you treated the string's length as a separate dimension, you got the equations for a graviton, the hypothetical quantum particle of gravity. Wait, what? A theory meant to describe nuclear forces accidentally gave us gravity? That was too weird to ignore. Physicists reworked string theory to explain gravity itself, and it turned out scale invariance was baked into the theory all along. This led to a jungle of string theories, until Ed Witten unified them under one big umbrella, M theory. And then in 1997, Juan Maldacena dropped the theoretical equivalent of a mic. Maldacena proposed something revolutionary, that a type of string theory in a 5D space, called anti-de Sitter space, is exactly equivalent to a conformal field theory in 4D, what we call ADS-CFT correspondence. Translation? Basically everything happens in this 5D curved space. Gravity, strings, black holes, and it can be described perfectly by a gravity-free field theory on its 4D boundary. It's like a cosmic video game. The full 3D plus 1 action happens in the game world, which is the bulk, but all the code lives on your flat 2D screen, which is the boundary, and the universe might actually work the same way. The implications for this are wild. First, the ADS CFT gave us a new way to resolve the black hole information paradox. If everything inside of a black hole has a mirror in the 2D surface theory, then information isn't lost, it's just stored differently. And second, this duality became a powerful calculation tool. When the physics in one description gets too hard to solve, you could flip to the dual theory where it's easier. And third, it may be telling us that something fundamental about the nature of reality, that gravity in space might be emergent phenomenon, illusions arising from a deeper, flatter quantum world. And here's the twist. The ADS CFT model doesn't describe our universe exactly. Our universe is an anti-de Sitter. It's closer to flat, or maybe even positively curved. And the math gets tricky when you try to generalize ADS CFT to our real cosmos. But physicists are working on it. They're looking for clues that holography might apply even in our universe. And we're already seeing hints of holographic ideas in everything from condensed matter physics to quantum gravity research. So maybe, just maybe, our entire 3D reality is a kind of shadow, cast by something simpler and lower dimensional beyond our reach. The holographic principle flips our intuition upside down. It challenges what it means for something to be real. It suggests that space, time, and even gravity might be emergent, like waves in water or pixels on a screen. Maybe we're not inside the universe, maybe we're on its edge, watching a 3D movie unfold. If you enjoyed diving into this reality-bending topic, hit that like button and subscribe for more deep dives into the wildest ideas in physics. And let us know in the comments, do you think the universe is a hologram? Or is it all just projection? Thanks for watching, and until next time, stay curious, and we'll see you on the next one.